Let me thank Alexei and everybody else who's involved in inviting me, and so I do appreciate the invitation quite a bit. And I'll also advertise the fact that I'm giving also a talk tomorrow, totally different topic in the Coniston seminar. So hopefully I can try the same crowd. So today I'm going to talk on symbolic-numeric computation of rational functions. I guess I'll switch keyboard here to move things back and forth. It's a joint work with Bernhard Beckmann and Anna Matos. And Beckmann is probably my main co-author. We've been co-authoring papers since 1992. So I don't think too many people have are lucky to have sort of co-authors that they've worked with for so long, and it's been quite productive. And Anna Matos, I've known almost the same amount of time. They're both from Lille, and in fact, those are the two experts in the particular topic I'm speaking about. I'm more of a peripheral player, and so lucky for me, it's the situation. Sometimes you just have luck. Okay. So today, what I'm going to talk about is I'm going to report on a paper on rational functions without Fossa double, and this is something that will be in archives shortly. And also on two related papers, one by Bernd and Anna on algebraic properties of robust pWeck approximates, and something by Gunay, Guttel, and Tofessen on robust pWeck approximation via SVD. The name Gunay is well known in computer algebra circles. Gaston Gunay was the co-founder of Maple, and but this is not Gaston Gunay, this is his son, Pedro. So it's kind of interesting. Okay. Okay, and the outline of my talk will be, we're going to talk about numerical analysis around pWeck approximates. I'll introduce what pWeck approximates are, sort of the numerical issues a bit more. We're going to talk about robust pWeck approximation, and talk a little bit about numerical analysis for general rational functions. I'll talk about comparing distances for rational functions. It's not so clear how to sort of separate when are two rational functions close. If you do numeric computation, you have to have the issue of when are two things close after you've done some numerical issues. I'll talk a little bit more about this Fossa double and what they are and the issues that come up. And I'm going to also talk, quite a bit of this work is by Bernd and Anna. And at the last, I'm sort of talking about, if I have time, I'll talk a little bit more about what they've done, and if not, I'll just sort of stop at the end of 5. So that's the plan of attack. So let me talk about numerical analysis around pWeck approximates. I don't know sort of if people are experienced with pWeck approximations. This is something that, for me, dates back to the start of my master's thesis, working on, at the time, matrix pWeck approximations. But in fact, the definition goes back to Pade in about 1890. Pade was a student of Hermite. And so what you're doing is you're given a power series, and you have a pWeck approximate, and two integers, m and n. It's mn pWeck approximate is a rational function p over q. P is first index is a degree bound for the numerator. N is the degree bound for the denominator. Of course, the denominator's got to be non-zero. And you have a sort of a linear relationship, fq minus p is basically a power series, and the power series is basically 0 up to a certain number of terms. And this terms depends on the degree itself. And what it's modeling is sort of taking a power series where you know a certain number of coefficients, and you say, can I find a rational function that when I do a Taylor's expansion of the rational function has the same number of terms at the start.
Where are the CJs?
CJs? The CJs are the coefficients of pardon?
Are they rational or integers?
In this case, they're complex numbers. Okay, but I've done, but they can be from any domain. They can be for integers. They can be rational numbers. They can be an exact arithmetic, or they can be an approximate arithmetic. In this case, it would be approximate arithmetic. So if you want to sort of know that, in fact, you can always find a pWeck approximation of degree m and n, type mn. Namely, you sort of take, if you take the last equation, the sort of pointer that I can It's fine. If you take the last equation up top there, then you have m plus n plus 1 equations, m plus n plus 2 unknowns. And so you have more equations than unknowns. You can always find a non-zero solution to such an object. And these equations are simply the equations of actually finding you first find the denominator. Again, one more equation than unknown. From that, you then find the numerator by multiplying f times q. And knowing that you only need the first m plus 1 coefficients. And so you can always solve this problem. And you can solve it even if you sort of encounter sort of indices where you might have some negative indices which just make zero. So it's just a convention like that.
So the method is Toeplitz matrix.
And these are Toeplitz matrices, that's right. Toeplitz. And so quite often when you work with Hankel or Toeplitz matrices, you can really represent it as something that has to do with Pade approximations. They're almost, there's a sort of a parallel machinery situated for both. Matter of fact, for Hankel matrices or Toeplitz matrices, if you want to find the inverse of those, in fact, there's formulas given in terms of numerators and denominators of Pade approximations. Okay? So they're very closely related. Uniqueness, yes, as long as you form P over Q. Obviously, there's many ways to solve this equation. And in fact, if you can find a Q, then obviously a Q and a P, then multiply by some constant, it's still a solution. So, but if you normalize the rational function itself, and you have a certain convention where you can sort of get uniqueness out of this, if you normalize properly. Scaling, quite often, especially in numeric computation, you like the coefficients to kind of you want to be able to control the input coefficients. And so you can rescale those input coefficients. You can rescale by taking z and replacing it by beta times z, or you can just replace each coefficient by multiplying it by a constant. That turns out to be something that's kind of vital. You tend to want to have the magnitude of your input be magnitude 1, if only because if you're looking at condition number matrix C, in this case it's a rectangular matrix, so you'd be looking at the magnitude of its a pseudo-inverse. In that case, quite often the condition number, you want to sort of forget about the magnitude of the input. You want to just have the magnitude of the inverse. And so that's what you're controlling when you're looking at condition numbers. So rescaling is very important. Okay. Also, when you're doing some of the analysis, it's quite helpful to sort of have things be inside a unit disk. Okay, Pade approximations sort of basically appear many places. Well, first of all, just the approximation of functions, where you have only a little bit of information. You have local information. You try and figure out, okay, well, when is this local information good enough to represent the function in an expanded way? Maybe you want to sort of understand what the singularities of a function are. Well, for a rational function, then the singularities will be sort of the poles, basically, and so that helps you, gives you some information. Inversion of structured matrices, I mentioned this comment about the Hankel-Toeplitz matrices, that you can have Pade approximations will give you the inverse formulas when they exist. Sparse polynomial interpolation makes heavy use of Pade approximations, not necessarily P over Q, but in fact it's the denominator. You find the roots of the denominator. They enter, at least via Prony's method, into sparse interpolation or exponential analysis. Quadrature formulas are basically the points of quadrature are also basically roots of a denominator for in a Pade approximation. Orthogonal polynomials are related to Pade approximation, many other type things. There's also other types of Pade approximates, simultaneous Pade, Hermite Pade, vector and matrix versions. The Hermite Pade or simultaneous Pade approximate turned out to be actually the main tool that Hermite used in the transcendence of E. So that was where they became a little bit prominent. Okay. Just for interest. Okay, one of the things that Pade was best known for is something called the Pade table. And so for any sort of numerator degree, any denominator degree, you can sort of form the rational function of something with a numerator having that degree and something having a denominator having that degree. And you can form the table. And what Pede noticed is that it has a certain structure. Namely, at a certain stage, you have a Pede approximation, and you have these rectangles, these squares actually, where the Pede approximation does not change in the entire square. Okay, where every rational function in this area is the same. And it all really sort of stems from the fact that at some level, you can sort of compute the rational function here, and then there's some criteria that says, okay, they're all the same here, and the next one will start at the next point. And these turn out to be kind of important. And so here, I'm isolating these a little bit. So these ones here and these, where one or more of the degrees are exact, is actually sort of a special Pede approximation. And we'll call them a non-degenerate approximate. And they turn out to play an important role in Pede approximation. So this sort of matches up example with a certain Hankel matrix being singular. And this is there, it's non-singular here, and it jumps to the next non-singular. So that's sort of the mathematics behind why you have this sort of common structure.
It's a bit like sub-resultant.
It's a bit like sub-resultants. As a matter of fact, sub-resultant sequence, extended Euclidean algorithm, and it's another way of computing Pede approximations when you reverse coefficients. And these gaps are the same thing as having degree drops. So that's exactly the same. Okay. So this is all in exact arithmetic. Everything is exactly very precise. Okay. Now, exact arithmetic, numeric arithmetic are sort of different beasts. And so all of a sudden, what you're really concerned about the fact that you have input of, now your input is a bunch of Taylor coefficients. And now you want to compute sort of a rational function which represents that particular function. But you want a certain stability. You want it so that small changes in these set of coefficients should somehow have small changes in the resulting rational function. Okay? So hopefully that makes sense. Undergraduate students here, for example, that should make sense, right? You have your input, you vary the input by only a little bit, and you do some computations. You don't want the output to be radically different than what you expect than the actual answer. It should be close. Okay?
The problem with converse reduction, if you change coefficients of the denominator, then it might cause large changes.
That's right. Yeah. So there's lots of issues there. So I'll mention that. And so actually there's two ways to look at this in numeric computation. One is forward conditioning. So if you give a slightly different input, okay, do you get, actually in Pede approximation there's kind of two ways of doing this. Then if you give a slightly different input, do you get a slightly different set of coefficients in the p's and the q's? Or, so that's kind of one side of the close by. And then there's the other side. And the other side is, well, now form the rational function, plug in a z. Okay. Do you get values that are kind of close to what you expect if you had precise coefficients? So either you have to measure closeness via coefficients or closeness via values. And the values could be single values or slightly different values in an entire region, typically a closed compact region. Okay, so hopefully that makes sense. So there's two different issues that come up in terms of trying to measure whether you're doing well. Okay. Background conditioning is now, it's sort of a, if you have a close by sort of, if you've approximated your input is just a little bit close by, now you get a rational function. Is this sort of a Pede approximation of somebody that's kind of close by your input? So it's kind of going backwards in this case. Okay. There's also an issue of what happens with the Pede poles, and this is something Bent and Jim Gulp quite a ways back. And it turns out their We did sort of a worst amplification of infinitesimally small relative errors, and turned out it was pretty bad. In fact, catastrophic, exponentially bad for the most part. Okay, so you're just studying the poles can be very bad. So the message is that there's two ways to sort of determine whether you have a good degree of accuracy. That's one thing. Well, there's forward stability and backward stability, but there's also sort of what you mentioned is good versus bad. That's important. And if you looked at only the poles, it's sort of a separate item. Okay. And that mainly occurs with sparse interpolation. It's mainly factor there. Okay. There are other numerical issues for Bethe approximations. There's something called spurious poles. These are sort of a numerical computation where these poles shouldn't exist. So in ordinary, in exact arithmetic, you do a Bethe approximation, you might have poles of the rational function, which are actually not really poles of the function itself. They're sort of far away from the singularities of the function, but they exist in exact arithmetic, mainly with algebraic functions. When you're taking algebraic functions and you're approximating with Bethe approximates, you can get something called these spurious poles. These poles that sort of exist as a rational function, but don't really exist as poles of the function itself. And I'm reminded, actually, when I gave sort of a little practice talk at Waterloo, and Southey Chen there at Waterloo mentioned that this is similar to having differential equations, linear differential equations, finding solutions where you have sort of apparent singularities, but they're not really singularities of solutions. So it's kind of very similar. Okay. So numerically, you have a little different situation. Numerically, you have sort of the situation where you have this Poisson doublet, and so here you have sort of a simple pole and zero combo. And in fact, you sort of have a situation where the pole and the zero are sort of nearby, and that sort of gives funny information about the function itself. Okay, so you want to make sure that zeros and poles are kind of separated enough so you can kind of tell that something really is a pole or not. Okay, so you want to make sure that a pole is really a pole. And then you also have poles that basically have a very small residual, so it's like a pole that pretends it's not a pole. So you have this numerical sort of issue about singularities of the function where it's trying to pretend it's not a singularity, but only because of numerical issues, not because of the function itself. Like having a small residual in exact arithmetic is no problem. Having a pole that's close by to zero in exact arithmetic is no problem. It's only a problem in a numeric computation where it sort of hides what's really going on. So let me talk a little bit about something called robust Bethe approximates, and this is the work of Gonnet, Gödel, and Travessen. And this is sort of what started Bent looking at a lot of this work. And so let me go back to the Bethe table. And there, what happens is that, so here, this one in red is kind of a little bit special. So what Gonnet et al. Are looking for in this case, when you're asking for a Bethe approximation of a certain type, they go, okay, so if you want to type m prime and m prime, that means you're looking for the yellow one. And in fact, what it's going to try and do is return the red one in numeric arithmetic. So it says, look, what I'm going to look for is somehow something where the degrees are exact, so something where it's equally distanced before, drop in numerator, drop in denominator. It's as if you pulled out a greatest common divisor. And it's going to return this rational function. It's going to call it a robust Bethe approximation. So again, here there's, in the green, there's cases where, for example, the numerator degree is correct. Here, the denominator degree is correct. Here, they're both correct. Okay. And in yellow, neither. So these are called non-degenerate, and this is called a robust Bethe approximation. Okay, and it's in a numeric computation is trying to work with these objects before. There's Cabet and Maleshko. Stan Cabet was my supervisor, actually. And he started a process where you sort of, if you're here, then in fact, if these are sort of ill-conditioned, no problem. They'll tell you how to jump to the next square, and he'll deal with petty approximations that way in a numeric environment. Okay, and there's also sort of a walk around these type of squares. Dealing with these squares is always what kills petty approximation, because this is where you determine zero or nearly singular. Nearly singular is always a problem for computation, numeric computation. Okay, so what Gonet et al. Did was, here's what they did. They took an input, a certain set of numerator degree, a denominator degree, the correct number of coefficients. And they said, well, look, I'm going to find you not necessarily the petty approximation with degree m prime and n prime, like you've asked. I'll find degrees which are smaller, and in fact, it'll be as large as possible. Okay. I'll solve a linear system of equations. I'll pull out a greatest common divisor when appropriate. And I'll take my matrix C and take the pseudo-inverse of the magnitude pseudo-inverse, and I'll make sure it's bigger than a certain tolerance. You ask for a certain tolerance, you put the degrees, the coefficients, and the tolerance, and I'll give you something which is the correct numerical rank of the degree of Toeplitz matrix. Okay, and from that point on, and the correct numerical rank, I can do the SVD on matrix C, and that'll find my numerical rank. And from that point on, I'll find the Q, and then from the Q, I'll find the P, and that rational function is the robust petty approximation. Okay, so it turns out that since I'm doing SVD, robust petty approximations are forward stable. And what was interesting is that Gonet, Gödel, and Trevessen sort of conjectured the fact that actually these robust petty approximations have no fossa doublé and no small residuals. And this is actually the starting point for the work of Bent and Anna back in about 2013 when they started. They looked at the paper and sort of found, first of all, these robust petty approximations interesting and important. And they try to understand, and they try to really see, does this really avoid these sort of these numerical anomalies? Is this the rational approximation that really will work properly for a set of coefficients for a function? Okay.
Excuse me, are these phenomena based on infinite precision arithmetic or not?
No, this is going to be finite precision arithmetic.
Finite precision.
Yeah, so that's the key, right? That's what makes it hard. Okay. Now, in the paper of Gonet and Gödel and Trevessen, this was in the SIAM review 3 years ago, they gave about 4 examples of petty approximation, and one is x function, one is a cosine function, and cosine function is squares of size 2. Exponential function is something called normal, where every rational function is different. But of course, at a certain stage, you reach a certain precision, and all of a sudden, these things become the same. So no longer do you have this sort of square-like structure, but you have a structure that it's a rational function under certain numeric computation, and then it just sort of stays the same. Okay. So these are just pictures from that particular paper. Okay. Let me talk a little bit about numerical analysis for general rational functions. I guess there we have some questions. For example, how to measure distance between rational functions. Okay, at some level, I mean, the question is sort of, you've got this question, but you have to figure out how to answer this. And the answer depends a little bit on how you want to represent rational functions. And at some level, it's a question of what you mean by close. Do you mean that when you form a rational function and you plug in some values of z, that you should always get values of z that are close? So if you've got 2 rational functions and you plug in the same values of z in a region and you're always close, does this make the rational functions close? Or does it mean that the vector of coefficients of the rational function is close? Again, it's not real clear which measure you should use. And even in the second one, you got the coefficients. What's your basis of polynomial functions are you sure? Are they monomials or are they Chebyshev polynomials? I mean, it's not so clear. Okay. When are two rational functions close? Okay. Another question that comes up, especially if you're using this for modeling. So if you're using this for modeling, rational function modeling, you use them in engineering for this sort of these feedback loops, and numerators sort of represent signals going in, denominators sort of represent signals coming back, this feedback part of it. And there, if you're going to model this, you really want a situation where you're choosing, you got to kind of determine when are the degrees. Correct. You want to sort of typically have a minimum set of degrees. To do this, the only thing that makes sense. Minimum amount of sort of variables really floating around. Okay, so there you're going to have to sort of, in a numeric environment, you're going to have to determine when a rational function is close to a rational function where the numerator and denominator have smaller degrees. Okay, so you have to be able to sort of somehow try and find that measure. And hopefully that distance should be far. So you're comfortable that, yes, I have a rational function with one of the degrees, numerator and denominator, being correct, and it's far away from things that are sort of incorrect. So that I safely say, yes, I've computed the right object. Okay. And then, of course, can you find a simple, reliable indicator that for Froissart doublés or small residuals that says, if this happens, we don't have those. And we have a true representative. So that's what you're kind of looking for. Hopefully that makes sense. For this section, it's always handy to have a sort of notations. So R and N to be sort of rational functions. P and Q, the degrees of P less than M, less than or equal to M. Degrees of denominator would be less than or equal to M. Rational function P over Q is non-degenerate if either the numerator or denominator, one of the two, at least one of the two has got correct degree. Exact degree. Okay. If both have smaller degree, then it's degenerate. Otherwise, it's non-degenerate. We look for non-degenerate. That's another way of saying that defect is 0. And defect is kind of a term, rational approximation appears a term. You say A1 is sort of dominated by A2. Means you kind of have small constants. Constants independent of the numerator and denominator degrees, such that A1 is less than A2, other than this constant and small power of M plus N plus 1. Small being, like it's like modest. What's modest in numerical computations? Well, it's one of the things where everyone knows it's the correct size, not too big. And A1 and A2 are approximately equivalent numerically if each one dominates the other. So at some level, they're kind of the right. Up to some small terms that don't mean too much, or you're not too worried much, they're kind of the same. D is the unit disk, which appears a lot in this type of computation. And if you have a polynomial, you can always find its vector coefficients, because you're doing a lot of linear algebra. And you work from polynomials or vectors or coefficients that kind of equal or common. You go back and forth a lot. Okay. Anytime you do an approximation or any rational function, the issue of, well, maybe there's common factors enters into it. Anytime there's common factors, there's a Sylvester matrix makes an appearance. We're all pretty, and here we want to have P and Q be relatively prime. So we want to find a Sylvester matrix with S star. A square matrix, we'd like it to be non-singular. That's kind of the thing we look for. So that's sort of something that's going to be of interest to us. So this Sylvester matrix makes a role. You can also sort of form a Sylvester type matrix, which is just going to be a little bit bigger. You're going to have basically two more columns and one more row. That also sort of appears more in pWeck approximation. Because again, you're going to have P times something plus Q times something is is basically 1. So, and the rational function is basically non-degenerate, not if S star is non-singular. In this case, it's going to be S is full rank. So that's basically what another factor that's been used by Gunet et al. When using SVD. Okay, and so it's full rank mainly because if you take away 2 columns and 1 row, you have a non-singular matrix. So you can reorder things and you make sure you get something full rank. Okay, as long as you're non-degenerate, as long as one of the highest coefficients is non-zero of P or Q. That's very important. Okay. So a long time ago, Bent and I wrote a paper on when are 2 polynomials, numeric polynomials, relatively prime. Okay, and that had been followed previously by a paper by Rob Corliss, Stephen Watt, and Patricia Gianni and Barry Traeger on sort of the numerical GCD problem. That's actually sort of the first place where the numerical GCD problem sort of entered into the ISAC community. Okay, we followed up by sort of basically Rob and them used SVD. We wanted to use more of a structured condition number as in SVD. So objects there was sort of then we have to sort of measure when you've got P and Q and when are sort of 2 polynomials relatively prime, or how close are they to 2 polynomials which aren't relatively prime? Okay, so we find this epsilon PQ, which is this value of the minimum distance from the vector of coefficients to another polynomial that had a common root. So that's the first line here. Okay. So when is P and Q sort of, how close is P and Q in terms of coefficients to another rational function where P and Q have something, a common factor removed, or have a closest common root. Okay, and another way to look at it is what's the distance from a Sylvester matrix to a nearby Sylvester matrix where the Sylvester matrix nearby is of lower rank. So it's kind of a structured condition number.
Wait, is that a typo or?
Where?
The SQP is that a
yeah, it's a typo. It should be PQ. It's a typo, sorry. Okay. And in this paper, we also sort of basically had a second type of structure where you take P and Q, and now you're kind of finding this sort of the smallest value of P and Q together in a certain magnitude, and which is kind of related to the condition number here. So the smallest value in a particular region. Okay. And there, so what we did at various stages is one is that, first of all, the epsilon PQ was the same thing, sort of basically the same thing as the smallest distance over the complex, extended complex plane of this infimum. It was computable. We could actually compute it in terms of sort of basically, given a PQ, we could sort of find the condition number of the associated Sylvester matrix by solving a particular equation. That was handy. And we could also show that basically the condition number kind of dominated the ratio of the size of the coefficients to this small epsilon number. Okay, so that was sort of something where we had something that was, this is computable and this epsilon was computable, and it told us something about the condition number. Structure condition. Okay. So here, I'm going to talk a little bit about the fact that you have a number of problems, a number of ways of measuring. You have a rational function P and Q, and you'd like to have no poisson double in the unit disk. You'd also like to have no small residuals in the unit disk. It turns out that you'd like to sort of have equivalence between measuring rational functions either by coefficients or by values. We kind of like to know if two things are small when you're comparing them in terms of values, that they're also small when you're comparing them in terms of coefficients. And something called this balanced spherical derivative in the unit disk also comes up, and it's kind of the equivalent of saying there's a small Lifshitz number, and so that turns out the integrated. And what Bent and Anna did was sort of said, look, if you have a well-conditioned Sylvester matrix, I can tell you about when there's no Poisson doublé in the unit disk. I can tell you when there's no small residuals in the unit disk. I can tell you when the bounded spherical derivative in the unit disk gives you information. And I can talk about when there's different, the fact that there's an equivalence between the measuring. And when I came into play, sort of now, naturally, again, if you got P and Q, you kind of want to know what numerical coprime is. And that says you want to know about sort of how does this measure this epsilon PQ enter into all these considerations. If you got sort of a small, if you got epsilon PQ instead of the condition number, does that tell you about the no Poisson doublé in the unit disk? Does it tell you about no small residuals in the unit disk? Is there information about the bounded spherical derivative? Is there information about the equivalent distance between rational functions? Okay. So that's sort of, so this is sort of, I have under contributions here with Bent and Anna, and Bent and Anna worked on this before. So that's sort of what happened there. And so that's what I'm talking about. Okay, and so that's sort of a lead-in for how to compare distance between rational functions. Because I mentioned here that again, sort of you talk about distances between, this is size of a particular function I'll talk about. Is it, what's the distance between one rational function and a close by rational function in terms of its values? And here's the distance between two rational functions in terms of its coefficients. Okay. So are those sort of equivalent measures? Okay. So for rational functions, okay, we're going to take its, going to find the coefficient vector. We're always going to take the fact that this XR, this vector, is have P and Q are going to have norm 1. And again, that's because in a lot of cases what we're doing is it's the equivalent of taking the Sylvester matrices, and if we look at condition numbers, we don't want to have the condition number, the input, we want to rescale things, so we're really looking at the inverse or the pseudo-inverse in this case. Okay, and there's sort of one thing to how to measure things. It's something called uniform chordal metric. You have a closed set inside the complex plane. You look at all the values measuring sort of two rational functions. They're like on the unit sphere, basically. And you're going to take the chordal distance between the two for all values. And you're going to find the largest distance between the two as measured on a unit sphere via this chordal metric. Okay, and the chordal metric is actually formally defined as this function. And it's the equivalent of taking two elements on a sphere and taking measuring the distance actually on the plane itself under after sort of stereographic projection onto the plane. That's how chordal metric really works. Okay, so that's how I'm going to measure values. Measuring coefficients, I'm going to take sort of basically values on the unit disk or on the unit sphere, and I'm going to sort of try to measure the separation between the two, but I'm going to have the correct phase. If it's on a sort of on a circle, it's kind of two rational functions either here or here, whichever one's closest. Okay? So I'm going to take the smallest distance to do where I'm going to worry about coefficient and phase, or phase and.
What is x allow? What is x allow?
X is going to be the rational function. Okay. I'm going to take two rational. Here is x of r, or x of r is the.
Oh, okay. Sorry, I forgot. Okay.
Okay. So it's a distance between. This time it's a distance between coefficients. A rational function p over q, another rational function sort of p hat, q hat, p tilde, q tilde. Look at the coefficients, compare them. They're each kind of a magnitude 1. Compare the coefficients properly. Okay, so how do you compare the distances? Again, let me put the chordal metric up and the d distance between the distance between values, difference between coefficients. And Anna and Bent show that, in fact, for as long as the rational function is non-degenerate, then the measuring distances with values versus measuring distances with coefficients really depend on the condition number of the Sylvester matrix, the extended Sylvester matrix. And at some level, if you throw in certain roots of unity, the correspondence is the same. So it says basically, if the condition number of the matrix is small or modest, then measuring distances with values, measuring distances with coefficients are basically equivalent. So that's sort of the main message that Bent and Anna were saying at that time. As long as the condition number is modest, and so they're saying if the thing you've computed comes from a well-conditioned system of linear system, which is of course what you want, because why would you be working with ill-conditioned system? You want to look at those cases where solving a linear system makes sense. And in those cases, distance by value, distance by coefficients kind of mean the same thing. Okay. And later on, we try to sort of do the same thing where now we wanted to do the relatively prime. So we want to replace condition number by more the structured condition number. And at some level, we could do it for the bound above, but and also for the bound below, but we had to stay with the condition number in this case. And basically, we had an example where it kind of didn't work the other way. So basically, the message is our indicator is the condition number, and this structure condition number didn't vary by very much. Matter of fact, if the condition number and the distance coefficients were kind of close, then the ratio of two condition numbers between one rational function and another rational function were also pretty similar. They didn't differ by much. And furthermore, again, if the distance between coefficients and the sort of distance from closest non-relatively prime polynomials is also not too far, then measuring sort of this structure condition number didn't vary much either between the two rational functions. And in fact, what this did also is it gave you a nice sort of situation where if you wanted to find the distance between one rational function and a rational function having numerator and denominator degree less than the particular value, i.e. from a non-degenerate to degenerate, where you like to have that distance be separated, then in fact it depends on the ratio, it sort of dominates the ratio of the structure condition number versus the condition number. Okay, so it gives you some measure of, if you measure that ratio, there's some distance that you could expect. Your rational function to the rational function kind of in a smaller domain, which you'd like to get some degree of certainty in those cases. In the case of Poisson doublet, recall there we have our situation is we want to have input. We want to have something a non-degenerate rational function. We're going to look at a closed disk or half plane, or else the whole complex plane. And we're going to sort of take a zero and a pole, and we're going to try and find a lower bound between the zero and the pole. We'd like that to be sort of not numerically fuzzy. That's basically the message. So how can we avoid sort of the interference between the two? And Bent and Anna said, look, 1 over the condition number, the distance is at least 1 over the condition number. And so that's at least when you start off with the non-determinate function, which is good. Okay. And actually the same is true if you have sort of a root, some estimate for a zero and root for some meromorphic function kind of nearby the rational function, not so far away in the chordal distance, the maximum distance. You can also say that basically the distance between the zero and the pole is significant. So at some level, we also thought that Poisson-Doublet should be linked with coprimers. At least for all 2 points there, we should have the chordal distance be at least sort of this bigger than or equal to the structure condition number divided by this sort of weighted sum of the coefficients. And so, because that's related to the condition number there. So here, in fact, if we want to take a closer look at Poisson-Doublets, then you can kind of look at this measure of a chordal metric of 2 rational functions compared to sort of the difference between, so if you take the 2 points z and w, and you map this rational function to its output, and you look at the difference between those 2 distances. Okay, so the ratio of the 2, the worst case ratio, is kind of a Lipschitz constant. Okay, so the quantity we have up there, the soup of chordal metric versus one of chordal metric of the output versus chordal metric of the input, is basically the Lipschitz constant, so the worst case Lipschitz constant. Okay, and in fact, if you let 2 points go close together, then you can kind of say, well, look, at this is at least equal to this vk of r, which is the basically sort of this quantity here, which is the spherical derivative of the rational function, times this sort of scaling factor, if you like. Okay. Then in fact, the Lipschitz constant is bigger than or equal to that number. So the spherical derivative also enters into this. Okay, but actually, in fact, the Lipschitz constant is actually bigger than or equal to pi over 2 times that Lipschitz constant. So they're kind of pretty closely related to okay. And then we sort of showed that, look, if a function is meromorphic, not too far away from the rational function, then this chordal metric between measuring the distance between a zero and a pole is at least as large as this Lipschitz constant, whatever this Lipschitz constant, which is at least the size of the spherical derivative. And also, if you have a simple pole, then the residual must be bigger than this spherical derivative or this sort of modified spherical derivative. Okay. So in fact, it sort of says, look, if you measure this spherical derivative, then you have a nice measure of this modified spherical derivative. You have this nice way of sort of saying, look, the zeros and the poles are separated, and the residual is not going to be close to 0. So you can avoid that situation where you've got something which is kind of a false pole in numerically. Okay. And if you wanted to know why the Lipschitz constant was bounded by pi over 2 of this modified spherical derivative, basically it's a very easy computation, which says your chordal metric of 2 rational functions is basically sort of less than or equal to the distance of the arc between 2 rational values, which you can compute via a curve from one point to the other. And you can bound it and get this sort of this nice ratio there. And this basically says that this divided into there is always like this. So the worst case is always like that too. Okay, so the fact is that this Lipschitz constant, this worst case ratio between that quantity and this quantity is always bound by here, using some simple, nice and simple argument. Okay, and then what else can I say about this particular theorem is that at some level, the last theorem it's a little bit sharper than before because of some comments. So here, just some properties that basically show that this is a little bit sharper than what we had in the previous statement. In any case, we did sort of want to point out that modest Labahns constant seems to be a reasonable thing when you compute. You don't want to have the ratio of your output be very different from your huge compared to your input. Otherwise, you can't really expect numerical correctness. Okay, and then just in summary, is sort of basically the one work that Anna and Bent did address this problem when the Sylvester matrix is well-conditioned. And here we sort of developed the same statements, but when we could sort of safely look at the structure condition number instead. And the structure condition number is something we could compute quite nicely and quickly. Okay. And in fact, I think at this stage, I think that that's reasonable to conclude the talk. I think. Suppose we get too much more technical details. Okay, so that's it for today.
I have a question about the Sylvester matrix.
Okay.
Is there any way that we can know if that is well conditioned?
Yeah, there is actually. So in that 1998 paper with Bent and myself, we gave a formula for the inverse of the matrix. And so therefore, if you normalize the matrix so it's magnitude 1, the condition number is the magnitude of its inverse. And we have a formula for the magnitude inverse in terms of computable quantities. And then we also gave a sort of a stable algorithm to compute the particular quantities at the same time, which is kind of like a Euclidean algorithm where you jump. It would be a computation as follows: take your Euclidean algorithm, you divide remainder into one remainder, and you just keep going to the extent Euclidean algorithm. So don't do that. But if you set that up as a linear system of equations, which solves the extended Euclidean algorithm all the way, then if you look at the associated linear system of coefficients, which is kind of a smaller Sylvester matrix, sometimes that matrix is going to be well-conditioned, sometimes it's going to be ill-conditioned. And we have an algorithm that says I can recognize when the Sylvester matrix is well-conditioned, and when it's ill-conditioned, I can jump. I can recognize when it's ill-conditioned, and in that case, don't use it as a subproblem. So always combine well-conditioned subproblems, well-conditioned subproblems in a remainder sequence. So jump those cases where the remainders lead to ill-conditioned linear systems of equations. And so you can deal with the condition numbers of Sylvester matrix and so on.
Which year is the paper that you mentioned?
1998 in Journal of Symbolic Computation. There's a special issue of something called I think it was the first SNAP conference, Symbolic-Numerical Algorithms for Polynomials. Might have been the second one. It was just before ISAC, 1996, in TEEP. Actually, it was in Inria and Sophie and Tiplis. Victor, I don't know if you were there. Did you come to, were you there in 1996?
Yeah, I was there.
You were there? Victor was there.
Even talked.
Yeah, so I gave the second talk because I arrived, prepared to talk the next day, and there had been trial arrangements screwed up with Rob Corliss, and Rob Corliss gave the second talk, but he wasn't there, so I quickly gave the second talk. Because it takes a lot of the nervousness away when you have 15 minutes to prepare your talk. And then, but you give your talk, and of course you're comfortable for the rest of the conference. It worked out very well, actually.
Historical landmark.
Yeah, it's a historical landmark, actually, and so that was nice. Any other questions? Tomorrow I'll talk about something far more algebraic, involving finite abelian groups and solving polynomial equations. Okay, everyone can come.
Yes, it seems that a condition number of Sylvester matrix is paramount, takes paramount roles in those numerical comparisons.
Sure. But a lot of it is also, I mean, you won't want to do this unless the condition number is modest. Otherwise, you really are solving a problem that you shouldn't be solving. So condition number of Sylvester matrix should be modest, and then you can start doing some of these proper comparisons. Otherwise, so we call it, inside Bent and Anna call these well-conditioned Peri approximations. In fact, what they proved also, I didn't discuss about, but can be proved also, in fact, is that well-conditioned, you can tell if full solid doublets shouldn't be there, and that no small residuals should be there. But there are examples of robust Peri approximations where there are full solid doublets and there are small residuals. So in fact, what Gonet et al. Thought robust Peri approximations were solved wasn't true. There are examples that were, that these things were encountered with robust Peri approximations. But what Bent and Anna then did says, well, look, for these well-conditioned things, I'll give you some measure where you can safely say, look, there's a separation.
It may lead to such research rule that if you want to study somehow numerically the approximation of problems, then you need to express them through Sylvester matrix.
Yeah, I think so. More than Hankel matrices. That's right, it has to be Sylvester matrices. But I mean, that's true also when you want to do fraction-free things like the GCD problems and subresolve. You can't do that. You can work with Hankel matrices, but in fact it's the wrong mechanism. You have to work with Sylvester matrices because there's a nice recursive structure when you do your computation. One Sylvester matrix, a big problem can be broken down into two two Sylvester type problems. And so that for recursive computation it's natural. Fraction-free computation, it's the way to do it, and also for numeric computation, it's essentially.
Hankel representation is not as good numerically.
Hankel is not as good numerically. You tend to have to go to the Sylvester. It's pretty natural, actually. If you think of GCD, Sylvester, it's very natural. Peri, not so much, because you've got A and then the other one is kind of 1. But in fact, you quickly get to the next computation where that sort of changes, and you should be going to Sylvester.
It's probably good for symbolic computation, but not for numerical.
Exactly. And even for symbolic computation, you tend to have to go from Hankel to Sylvester anyway. It's really the same.
Could you say a few words about the not-applying error?
The which one?
The one of the...
Yeah. So what happens is says you can't. So we couldn't really say that if they're kind of numerically relatively prime, that in fact that we get something better than here about the distance between the two measures, that distance by value versus distance by coefficients. We couldn't really improve on that. So we could use a structure.
Couldn't prove. Doesn't mean it
No, matter of fact, we had an example that basically sort of said that here this says that they're kind of comparable. But here, we sort of couldn't replace it. We had to go back to the condition number.
And the importance about the coprime measurement.
It's basically structured.
It's easier to compute that than the condition number.
It's a structured condition number. So in fact, it's a better measure because it's a structured condition number. It's easy to compute, and it's better than sort of the ordinary condition number, which you can compute the ordinary condition number, but the coprimus one is a better measure, easier to compute and more accurate. Because again, it's finding the distance to the structure problem, as opposed to the ordinary condition number, which is sort of takes your linear problem and says, look, find it the closest to any matrix. So really, the distance from the structure, your Sylvester matrix to any singular matrix is going to be much smaller than the distance from Sylvester matrix to the next singular Sylvester matrix. So you have to go further to find that. So that means we can widen our abilities to find when things are numerically relative to prime, for example.
There is, of course, a big question how it's possible to apply this study to approximate polynomial GCD and get some progress.
Yeah.
But it's too
Well, we did that's right.